If you don't hear me, then you can put your question on a chat. And I'm just trying to share the screen. My first question is, have you been able to go through the decks that I had sent earlier? You can probably respond in the chat, or you can even respond by audio. I just need to get a feel. This poll is a very complicated and cumbersome thing we tried yesterday. I don't want to try that today. Question number one is, are you all able to hear? And question number two is, were you able to go over the decks? You can type in your message in the chat. I'm not seeing any messages in the chat.
We could go through few decks and we could solve few questions.
Okay.
Not all.
Okay. Yesterday I had discussed one Excel sheet, and I had said that there are a few mistakes. Were any of you able to find out any? In what I call as the motor spec calculator, I had just hurriedly put together the deck in order to give you all a flavor, the Excel sheet in order to give you all a flavor. And there were some mistakes. I knew there were mistakes. And I only wanted some of you to discover the mistakes and tell me what the mistakes are. Are you all able to see the screen? Can you see the screen I'm sharing?
Yes, sir. Screen is visible. Yes.
Okay. So I want you to all rework this screen, this sheet, which I already sent by email to you. At each of the operating points, the operating point is one where a particular kind of operation is expected from the motor. And there are 4 different operating points I have listed here. One is how it should operate in acceleration, how it should operate in a peak speed region, and another is what performance is expected when it is starting from a slope, and the other is when it's climbing uphill. And I have also yesterday given you the equations that govern the different behaviors. And actually what you must do is that for each of the operating points, there will be all the 4 components of force have to be considered. The 4 components of force are rolling resistance, air drag. Can you see where I'm pointing with the cursor? There is rolling resistance, there is air drag, there is climbing force, and then the remaining force which is used for acceleration. Are you able to see the cursor as I am pointing, or would you want me to zoom? Let me zoom it a bit. And this is what I had written yesterday. I don't know if you have noted this down. And if you notice my workings, I have not considered all of these forces at each of the operating points. For example, I have considered in acceleration the force required to accelerate. I have also considered the air drag that will be encountered when it has reached the final speed at the end of acceleration, but I have not taken into account the rolling resistance. And likewise, if you see at the peak speed, I have considered the air drag, and when it has reached peak speed, there is no further acceleration, so we need not consider acceleration. and the peak speed is going at a uniform level road, so there is no climbing force. But the force that I have not considered here is the rolling resistance, which must be added in. So only after I add both those forces, I can do the rest of the calculation. Likewise, in each of those, you can see that there are some forces I have considered and some forces I have not considered. Some forces are not considered because they are zero, but some other forces which are non-zero also I have not considered. You have to amend your sheet accordingly. Do any of you have any questions about this? If you have any questions, you can tell me. I'm trying to get into the place where I can see the chat window, but I'm not able to see. Okay. I think unless I stop the sharing, I cannot see anything else. Let me do that. Okay. So do any of you have any questions about this sheet? You can answer yes or no, but I'm just waiting for some response.
Sir, this graph should change dynamically whenever we change the parameters, or
Yes, yes,
it
yes,
will change dynamically.
Yes, all the numbers are linked.
Okay.
Yeah. Again, that may or may not be, you can check up, because I may have, from the cells from where I have generated the graph, maybe I have simply keyed in the numbers without linking them. But if you change that by linking it, then it should change dynamically. I can check that right away if you want.
I'm changing acceleration from rest to that from 40 to some 80, and trying to see the effect, but it's at present it is not changing actually. Gear ratio I'm trying to change.
To figure that out, you have to go to the graph and see where it is picking the numbers from.
All
and
right.
do you know how to do that in Excel? If you simply click on the graph, the cells that get shaded are over here in the columns K, L, etc. Those are that is where the numbers have been picked from. And if I go to any of the cells there, for example, I'm going to the RPM, then if I click on that cell, it is just a number that is entered over here. Where did this number come from? It has actually come from 1326 RPM. It's climbing at 7 degrees. If I scroll down and see climbing, then it is here. I've simply seen this number and copied it there. If I don't do that, and instead if I go to this cell and say it is equal to, and I link it with the cell below, like this, and like this, if I do for every cell here in this table, then the graph will change dynamically.
Okay, okay, sir. Thank you.
So let me stop sharing for a moment. The topic I wanted to actually cover today has to do with the other Excel sheet that I had shared with you. And do you all have the Excel sheet with you? Of course, you will be able to significantly follow the Excel sheet only if you understand everything in the decks. But even if you don't understand everything today, I thought let me go over it and give you all a flavor of it, because then later on you can always review the deck, and you can also dip into the video whenever you have a difficulty in following the deck. And and you will then be able to understand the logic of this Excel sheet. So I'm going to go directly into the Excel sheet. Unless any of you have any doubts about the deck that you have seen, and about the assignments that you have seen. If you want any doubts to be clarified, let me know. Otherwise, I'm going to plunge straight away into this Excel sheet. Is there anything that you would all like to ask me? So again, I cannot see any responses in the chat window unless I stop sharing. I haven't found any responses in the chat window. Shall we proceed with the other Excel sheet? And my other question before proceeding is, this will be more like a workshop session. I will be expecting a lot of you to work out things. Do you have Excel installed with the two functions that I had mentioned? One is goal seek and the other is the solver. If any of you don't have it, let me know. How many of you have installed solver?
Sir, that solver is installed as it was instructed in your email. Okay. So accordingly, we have installed the plugins.
Excellent, excellent. So you have goal seek and solver. So let me then go ahead with that. I will share the screen and I'll first tell you about the way the whole thing is architected. If you go to this README tab, I will need to probably reduce the zoom so that you can see everything. Yeah. So what we have done here is that we have tried to organize the overall motor design, and the controller algorithm will actually follow from the motor design. So you cannot separately go to a market and buy any controller and then connect it with any motor and expect it to run, unless the controller and its both hardware and software are specifically designed for a particular motor, configured for a particular motor at least. The two will not run together, although each of them may be individually proper products. So this is why it becomes a challenge to simply go to any random marketplace and buy motors and controllers. They have to be compatible with each other. And to understand what are the parameters of a motor, which then will take effect in the software, you will need to understand this block diagram. The design of a motor comes from its geometry and the material selection. That is what the top block says. And from the geometry and the materials, I can derive what are called the electromagnetic properties, and I can also develop a thermal circuit that describes the design. So if I look at how I can get the electromagnetic properties, one simple, straightforward way to do it is, if I have got a motor with me physically on my table, then I can measure all of these. P is the number of poles, Xi is the strength of the magnet, and LD and LQ are the inductances in the principal axis, and RS is the resistance of the armature or the windings. And all of these can be these parameters. The last four parameters can be measured using different instruments. Resistance can be measured using a sensitive ohm meter. LD and LQ are measured using what is called an LCR meter, and Xi can be measured using what is called a Gauss meter, and P is simply the number of pole pairs. I have to open up the motor and count the number of magnets that are there, and that is the number of poles, and that divided by 2 is the number of pole pairs. So if I have a motor with me in hand, then it is easy to get all these numbers. But if I don't have the motor with me, it's only a motor that I have designed or somebody has designed. I have the drawing, of the motor. It has not yet been built. And along with the drawing, I have all the material specifications, that the different parts which are there in the drawing are made of certain materials. If there is a magnet, I know what is the strength of the magnet, what is the material of the magnet. If there is steel, I know what's the grade of steel, and so on. If I have all this information, then I can do what is called finite element analysis, FEA. That is what is written over here. I can do FEA and infer all of these values. And again, from the geometry of the motor and the material properties of the different parts that are there in the motor, I can cast the entire motor as a thermal circuit through which heat will flow in different paths, and in each path I can calculate what is the thermal resistance. And the reason why I have written the electromagnetic and the thermal at the same level in the hierarchy in this block diagram is because each of them will influence the other. For example, if the thermal circuit is such that in a particular operating condition, if the temperature is going to rise, then two things will happen. One is, because the temperature is rising, the resistance of the windings will also increase, because the resistance of any conductor has what is called a thermal temperature coefficient. At higher temperatures, the resistance will increase. Likewise, if the temperature increases, magnet also becomes weaker. So there is a negative temperature coefficient for the magnet, and the magnet will get progressively weaker as the temperature increases. And the resistance increasing means even more heat will be generated. So it becomes like a positive feedback. Because the temperature is higher, the resistance will increase. Because the resistance is increasing, I'll get more heat. And because I'm getting more heat, the temperature will rise still further. So it can be a very catastrophic thing. It will normally settle down at a much higher temperature than we would have expected. But sometimes it may just get into a runaway cycle where the temperature goes beyond the specified limits, and then the whole thing will either burn or it will shut down. So we have to be very careful about the thermal effect. And even if the whole thing does settle down at a higher temperature limit, what will happen is that the magnets become weaker, and so the motor will perform much poorer. It will give much lesser torque. It will be a much weaker motor than we thought it is. And this is again a consequence of the temperature effect. So the thermal and the electromagnetic have a close interplay with each other, and we have to appreciate that. And so once I have figured out the electromagnetic and the thermal circuit related parameters of the design, then the performance of the motor depends upon what is called the operating point, which means what is the condition in which I am operating it. So I may operate it by supplying it more current, or I may try to operate it at high speed. And if you have seen the deck, you know that there is a very, very important parameter in the software, which is called the phase advance angle. And how much of phase advance angle I am providing will again decide how the motor is going to perform. And then where I am running the motor, it's in an environment where there is a certain ambient temperature, and the air around the motor is blowing at a certain speed. Sometimes the air may be blowing because of a fan. In some other circumstances, maybe it is just mounted on a vehicle and the vehicle is traveling. So relative to the vehicle, air is blowing in the opposite side. That can also contribute to air speed. So all of these things will influence the actual performance of the motor. So the design related parameters are given in the top, the EMAG and the thermal, and the operating condition related parameters are given in the operating point block, and together they will all decide what kind of performance I will get. And the performance I'm interested in is in knowing how much torque I will get, what will be the losses, what will be the efficiency, what will be the voltage, and so on. So this is how the whole thing is architected. So far, if you have any questions about what I'm showing here, please ask me. Otherwise, we will get into the detailed sheets and how the calculations are done. Are there any questions? Yeah.
Hello?
Yeah.
Sir, I am hearing you.
Yes, I can hear you. Please tell me.
Yes, sir. Sir, I am Praveen from Geetanjali College of Engineering and Technology, Hyderabad.
Okay.
Sir, my question is, now you show some pictorial view of the design of motor, right?
Yeah.
So the design of motor is based upon the capacity carrying of the vehicle, or only the frame weight carrying of the vehicle?
It depends on what is
Which,
called the gross vehicle weight. So gross
okay.
vehicle weight includes the empty vehicle plus all the passengers and cargo that will go into it.
Okay, so suppose we prepare some of the vehicle on 10 ton or 20 ton. So
Okay.
when we use that vehicle to travel on a slope areas, uphills or downhills, so at
Yeah.
that moment, our design specifications you told to me, told and yesterday and today, for only for the grass weights of empties and loading and unloading positions. So suppose in uphills drive, then it will be efficiently to pick the vehicle from down to up.
Yeah. If you have designed the vehicle to travel, for example, the other Excel sheet that I showed you a short while ago, which was discussed yesterday,
Yes.
there the requirement was that the full gross vehicle weight must be able to climb a hill at 15 kilometers per hour with a slope of 7 degrees.
So, sir, another one is in our conventional vehicles, means in petrol drive or diesel drive, during acceleration, the rate of speed will be changed accordingly to up to the maximum speed,
Okay.
right, sir? So
Mm.
same way here also we can possible to maintain that type. Suppose we need it less, and it will take sudden pickup on the high speed.
Yeah, yeah. All that depends
It's
upon the driver
possible on.
control. Yeah, driver's control. Correct. So
It's
the,
possible to take high peak in immediately.
yes. So if I show you the Excel sheet once again, let me just share that. I'll explain to you where that control comes from. Um, yeah. So I have given here that the
Yes,
operating
sir.
point is normally decided by the user. How fast he
Okay.
wants to go and how much acceleration. Acceleration is related to the current.
Yes, sir. We.
So if I turn a throttle, I'm actually giving a signal to the controller that this is the acceleration I want.
Oh.
The more I turn it, more the current that will be supplied.
Yes, sir. My question is, it suddenly take the pickup, means
Yeah,
instantly. Same way in conventional vehicles, is when you are accelerating it more, it suddenly is to take the act engine accordingly to take the suction on all those things, right? Same way
yeah,
here also, it will possible to take sudden peaks and sudden drops of the speed.
absolutely. In fact, it will be much more responsive than an IC engine, much faster response.
Okay, sir. Thank you. Thank you, sir.
Okay. So, are there any other questions about this block diagram?
No, sir. Sir, I have one small request for the main host, means program head. Sir, I registered in a WebEx KOLA, but I didn't check that whenever I typed then it will comes KOA. So please consider my request to consider my attendance for Kola Praveen. Aryabhatta, sir. Hello.
Yeah.
So please consider that.
So,
That's
yeah,
the thing.
that should be fine. I don't think there's a problem. You just send him a mail and that will be taken into account. No problem. So, are
Okay.
there any other questions about this?
No, sir. Thank you, sir.
Yeah. So, let me again check whether there are any questions on the chat window. I don't find any questions. If you don't have any questions, then I'll move on. The subsequent tabs I'm going to discuss will be somewhat involved. Again, as I said, unless you have a fundamental conceptual understanding, which comes from understanding the decks that have been shared. You will not be able to share, you will not be able to follow most of what I'm saying, but it doesn't matter. Those of you who have not found the time, because the idea of flipped classroom is that. The idea of flipped classroom is that 90% of the work has been done by you before coming for the session. And in the session also, most of the work will be done by you, not by someone like me. But if you have not done it, you can always do it subsequently, and you can communicate with me on email if you need any help. So let me go to the sheet again. So let me go to the electromagnetic tab, which is the next tab. All of you can open that. And I don't know if you're all able to also work on the Excel sheet as you see what I'm saying and look at the screen, because I'll be giving you exercises to do as I'm talking, so that you become familiar with how to use this tool. Is it possible for you all to do it? Because I'm finding that unless I stop sharing, I can't do anything else on this computer. But you must be able to work on the Excel sheet even as you are seeing what I'm doing. Is that possible or not possible? Can any of you tell me?
In my view, it's possible, sir.
You are able to work on the Excel sheet.
Yes, sir.
Okay, that's excellent. Very good. So here I'm showing you a motor. Let's take for the moment that that motor was given to me by somebody, and I have opened up the motor. I see that there are 10 magnets. Therefore, I am saying that the number of pole pairs is 5. And then I put together the motor again, and using an LCR meter, I have measured the LD and the LQ as 70 and 120 microhenry, and I can apply, I can pull out the magnet from the rotor, any one magnet, and measure its strength using a Gauss meter. And I find that the magnet strength is 0.012 Webers. And I can also measure the resistance. It is 25 milliohms. Yeah, somebody has a question? Is there any question? No. Okay. So if you notice, these parameters 1, 2, 3, 4, 5, these 5 parameters have been given the flag called spec. Spec is something which comes from the design of the motor. If you change anything here, it means you are changing the design of the motor, or it means you're picking up a different motor for investigation. So once a motor has been built, the spec cannot change. Please remember that. Again, I can take you to the previous tab. All things that come from the design are flagged as spec. All the things that come from the choice of the user about how to operate the motor, they come under input. And everything that comes from the behavior that results as a result of the design and as a result of the choices made by the user, the motor then behaves in a certain way, and all the parameters of behavior are called the output. So these are the 3 flags we'll be using. Please pay a lot of attention to these 3 flags: spec, input, and output. And don't mix them up. In particular, don't enter any value through the keyboard wherever you find output, because output will come from formulas. If you enter a value there, then you're destroying the formula and you can never get it back. Then the entire Excel sheet will collapse. It's no longer a useful tool. So be very mindful of that. Now, and this entire sheet, all the tabs have been organized in blocks which are related to each other. Now, I also told you that the thermal effects will influence the electromagnetic effects. So in this block, we are dealing with that. I told you that I measured the resistance and the LD and the LQ and the Xi, etc. of the motor before starting to use it. And these are the values that I got when I was measuring. Now I'm measuring all these things in a nice air-conditioned laboratory where all these instruments are there. And I noticed that the room temperature in that room where I measured is 27 degrees. But later on, when I am running the motor in a vehicle on the road, the temperature is likely to be much higher. It may even be 100 degrees or even more. I don't know what it is, but based on my guesswork, I can change it to anything that I think it will be. And later on, when I find out what it actually is, I can correct it. So I will tell you the correction part later, but right now, I am assuming that it is, let us say, 80 degrees Celsius. I'm entering here 80. I want you all to enter 80 in your sheets. And before entering, I should always check whether what is here is a formula or a number. When it was 63, I'll just do Control Z. Yeah, it is just a number. Now it's a number with some very large number of digits. Why it came like that, I'll tell you later. But finally, it's a number. It's not a formula. What is entered here is a number. If it's a number, it is safe for me to change it. But if there is a formula and I write a number, then I'm overwriting the formula, then the sheet becomes unusable. Please keep that in mind. Another way of checking is it an input or is it an output? If it's a spec, I can change it. If it's an input, I can change it. But if it is an output, there will be a formula. If I go to the next line, the formula. Now I cannot, supposing I don't like this number 28.56. I wish it were 30. Then I cannot go here and just enter 30. If I enter 30, then this formula will go. And I can never recover it. So anything that is in an output field, don't change it. Is that clear? So I'm assuming now, okay, now I want you all to notice that when the number here is 63, the resistance is 28.56 and the operating magnetic strength, magnetic flux linkage is 0.0115. For the sake of reference, let me write those two numbers here, 28.56 and 0.0115. I've just copied these two numbers here. But these numbers are coming from some formulas. The use of the word operating here means these are the numbers that are actually there in the operating condition chosen by the user. So if you notice, the resistance when I measured in the lab was only 25 degrees. But when the temperature increased to 63 degrees, the resistance has increased. The operating resistance has become 28.56. Is this clear? Same way, the strength of the magnet was 0.012 at 27 degrees. But when the temperature increased to 63 degrees, the magnet has become weaker. It has become 0.0115 instead of 120. It has become less strong than before and the resistance has increased. Can you all see this? Now, if I say that the winding temperature that I am assuming is actually 80, see what happens to these two values? The resistance increases even more and the magnet strength falls even more. So can you all see this? And so far, if you have any doubts, please ask me. I'm taking you step by step. So I am seeing that somebody says they're on mobile. It's not possible. If you're on mobile, you cannot participate in a workshop. I told you that there's a flipped classroom. You have to
30 of the participants are on a mobile device.
Majority are on mobiles.
Not
If it-
majority, but 30 out of 70.
30 out of 70. If you're on a mobile, you cannot be doing a workshop because this is going to be a very hands-on practical workshop. It's not a lecture. I told you yesterday. It is a flipped classroom. You will have to do all the work. I'll only be telling you how to do the work, but you have to do the work. You must work on a laptop. Thank you. Thank you very much. Okay. Yeah. So the session will be pretty unproductive if you have come here thinking that you're going to listen to somebody. You're not listening. You're actually going to be working. All the time you have to be working. Otherwise, you will not get anything out of the session. So let me move on. So now I'm coming to the next block where the relationship between torque and current is examined. Again, if you have attended the lecture videos and if you have seen the text that I have shared, you will know that current and torque are related. The torque does not depend upon the voltage. The torque depends only on the current. The other thing that you will also know is that the speed does not depend on the current. Speed depends upon the voltage. So there is a torque versus current relationship block here. And then there is a speed versus voltage relationship block below it. Again, whatever is given as the input is what the user can change. For example, by turning the throttle, the user can set the amount of current that will flow, and based on the current, torque will be produced. Based on the torque, acceleration will happen. So when I turn the throttle more, I'll get more acceleration. If I turn the throttle less, I'll get less acceleration. Is this fine? And allied with the turning of the throttle, which defines the current, the software in the controller will decide what is the phase angle. It may decide what is the phase angle depending upon the code that we have written and what should be the phase angle. How should we write the code so that it gives the best possible phase angle is again something that I have discussed in the lectures in the deck that I have shared with you. And that algorithm is called MTPA, maximum torque per ampere. And I won't be able to go through all those things because I expect you to study them yourself using the material that I have provided. But I'm just pointing out that the angle that comes out from that algorithm is what is entered here as an input. Only thing is this input is coming from the software, it's not coming from the user. Whereas the current as an input is coming from the user who is the driver who is turning the throttle. So again, let me stop sharing for a moment to give you all a chance to ask any questions. I'm also looking at the chat window. There aren't any questions. If you don't have any further questions, I'll proceed further. If you want something to be explained so far, you can pause me and ask me. So let's get back to this. Now, based on the current and the phase angle combination, what is called the ID and IQ, the currents in the DQ frame of reference get set, and based on the IQ current, the magnetic torque will get decided based on the ID current and the IQ current, both of them together. You can see the formula here. The reluctance torque will get set, and the total torque will actually be the sum of these two. But if you add 4.1 and 0.2, let me do that here for your understanding. If I say it is equal to, you know that the total torque is equal to magnetic torque plus reluctance torque. Those of you who have seen the lectures will know that the sum of the magnetic torque and the reluctance torque is the total torque, but the total torque that is given here is somewhat lesser. And I need to explain to you the reason for it. The total torque that we refer to here is called the electromagnetic torque. And part of this electromagnetic torque will be consumed by the steel losses. And after deducting the steel losses, what I get is this, and that is called the shaft torque. And shaft torque is the useful torque that is getting delivered to the vehicle. The useful torque that is developed by the motor is the electromagnetic torque. The steel losses consume a part of it, and the result is the finally whatever is left over after the steel consumes some of the torque is what is getting applied to the vehicle, and that is called the shaft torque, and that is equal to 4.2. So now if you click on the cell 4.2, you will find that it is E19 plus E20, which is the magnetic torque plus the reluctance torque, minus there is another term, which if you scroll down, you can scroll down. Those of you who are working on the Excel can scroll down. You will see that it is related to the steel loss. And steel loss is given in watts, that is E34. And so I can say that the steel loss is some kind of a measure of power. The steel consumes some power. But what I'm interested in knowing is how much torque loss will it result in. So you all know that power is equal to torque into speed. And so power is equal to torque into speed. I know the power that's given in the E34 cell as a steel loss. If I divide it by the speed, then I'll get the torque. But remember, the important thing is when I divide by speed, speed has to be in the correct units. It has to be in radians per second. It should not be in RPM. So what we do is E28 is the speed in E34. Okay, I'm sorry, I think I made a mistake. E34 is the, E28. Okay, E28 is over here. E28 is the speed. So divided by speed, I have to multiply the speed by 9.55. Actually, I have to divide the speed by 9.55. But since the speed is already in the denominator, dividing the denominator by 9.55 is the same as multiplying the numerator by 9.55. So if I do that, I'm essentially converting the RPM into radians per second. So this is the amount of torque loss that the steel losses will deliver me. So after I subtract that, I get the shaft torque. Is this clear so far? Please remember that this session is a flipped classroom. You have to work out things. You have to use the Excel, and it assumes that you already studied all the chapters that have been given to you. So I'm really targeting the session at those who have done that. Those who have not done it will find things difficult to understand, but try to understand what you can, and later on catch up on all the material that you have to catch up. And you are welcome to get back to me later also with any doubts that you may have. So if there are any doubts so far, please ask me. And I'm just trying to see how many participants are there. Today there are 66. Okay.
Hello, sir.
Yeah.
Sir, you shown the Excel sheets will be in ISO standard or any other standards to take, or your own to prepare that?
I have shared the Excel sheet already with you by email.
Yes, sir. I have. The prepared Excel sheet as your own, or it will be international standards or Indian standards made?
It is a sheet that is invented by me. Nobody else in the world has it. So I'm sharing it with you. So there's no
Yes, sir.
standard.
Sir,
The standard is only made by me.
Congratulations also, sir. Sir, the sheet will be given more information because at last semester we are preparing some electrical car, means four seater capacity, but we are not analyzing such things. Just we take some go to the market and bring something, means in electrical shops or all those things, we're searching it and then purchase something else for running of that vehicle.
Yes, I have found that most people don't have a systematic approach to designing anything.
Yes, sir.
So people are just randomly.
Pick something
It's
and then
like, yeah, it's like going to a hotel and looking at a menu and ordering something, and then later on you get a stomach upset. So this is how
yes, sir,
design happens.
same thing.
This is how
Same
design
thing we
happens.
are facing, sir. We purchased two batteries, around 2 lakhs rupees are wasted.
Yeah. So this Excel sheet is meant to help you understand the concepts and apply them systematically so that whatever you do, you get the right results that you're targeting. And if you're not going to get the right result, you know it at the design stage itself before you spend any money.
Yes, sir.
And the only other thing that people do when they try to design is that they go and purchase a software that costs 35 lakh rupees, sold by big companies like Siemens and all that.
Yes,
And those softwares are very attractive to look at visually, but they don't give us any understanding. So it is like a black box. There is in software, there is an abbreviation called GIGO. I don't know how many of you have heard of this word called GIGO, GIGO. It is like garbage in, garbage out. So people who understand nothing about the design, they simply plug in some numbers into that software and then try to execute the software and then see what results come. Whether the results that come out of it, for example, I will say that I have a magnet of such and such strength. I have the diameter of the rotor to be so big. I have 8 pole pairs. Without understanding what is the impact of each of these choices, and then I simply put it in the software and think that that software will magically tell me how the motor will work. And obviously, the software is correct. I'm not saying the software is incorrect, but the software will give some random results, and those results won't match what we need. And if it doesn't match, then it becomes like what is called a Monte Carlo technique. I don't know how many of you have heard of the word Monte Carlo technique in mathematics.
no,
Do you
sir,
know?
sir. What's about that?
So in mathematics, there is a class of algorithms or methods called Monte Carlo techniques. It is named after a town in US which is famous as a gambling den. So without understanding anything, if you simply randomly try, but if you try a million times, then you are likely to get the correct answer one time. So this is how people use the software. It's like a Monte Carlo approach. I will throw some numbers, I'll see what the result is, then again I change it. I keep on doing multiple times. I will make some 100 trials without understanding what is the impact of any of the inputs I'm giving, and then hope that sometime or the other I'll get a result which is acceptable. This is how people do design. So about 10% of the people try to do design. The remaining 90% of people simply pick up something from the market and try to put things together. Even those who do design do it using this Monte Carlo approach by investing in some expensive software, which doesn't take us anywhere. So this tool, this Excel sheet, is actually worth more than 35 lakh rupees. Whenever you get a good result and build a car, I want you to pay me 35 lakh rupees. But till then, the tool is free. Okay.
Sir, we are prepared, but the vehicle will move on a flat area, not in slope areas.
You can use
Not to take the
you can use this to design any kind of vehicle. We're using it to design drones.
Yes, sir.
We will also use it to design Mars rovers. To the extent the Mars rover will run on a battery. Unfortunately, Mars rovers don't run on battery; they run on jet fuel. So, but anything that runs on motor, we can use this to design.
Yes, sir, okay, sir. Thank you, sir, for your share the Excel sheet to me and all the participants also.
Yeah. So I'll go on. I'll just show you how to use the Excel sheet in a productive way. Whatever you don't understand, please make it a point that later on you will look at the lessons shared and understand it better. So I'm
Okay,
coming back to the Excel sheet, and you can see that in this block, there is only torque and current. So it is neatly arranged as a separate block without messing it with anything else. And so based on the current I choose and the angle that is computed by the software, I know what is the current. And only thing is, this angle which is computed by the software, if the software computes it incorrectly, then I will not get this torque. For example, you are seeing here that the torque is 4.2. Now, if you have gone through the lessons, you will know that this angle can be anything between 0 and negative 45. It cannot be positive. If it becomes positive, it will give very bad results. So this is common sense. We all know that it has to be some number between 0 and minus 45. What we don't know is that it must be minus 11.6. So when I am designing a motor, I am yet to design the controller. How do I find out that this angle should be 11.6? The way I can find out is, I can do it by trial and error. I want you to change it as I'm doing now. You just go to the cell and change it as minus. Before that, you notice that the torque here is 4.2. Okay. Having seen that at minus 11.6, I will also write it here. Minus 11.6 is a number. I'm going to change it. So for future reference, I'm writing it here. If it is minus 11.6 and I now change it to say minus 20 degrees and hit enter, then you can see that the torque has become lesser. From minus 11.6, if I make it minus 20, the torque has become lesser. But what if I change minus 11.6 in the opposite direction? Instead of making it more negative, I'll make it less negative. So I can put some number like minus 2 degrees. Then also I get less. So no matter whether I increase this angle more in the negative direction or decrease it in the negative direction, I will never get a better torque than what I get at 11.6, which is 4.2. If I put back here minus 11.6, I'll get minus 4. I'll get 4.2 as a torque. Now, if I have to do this optimization through trial and error, it becomes a very troublesome thing. It takes a lot of time. So what I will do is, normally when I'm designing, I have not yet designed my controller, so I don't have a software which is going to tell me what the correct angle is. I have to find out everything using the Excel. So whatever the software does, or the software is going to do after you write it correctly, you can find it out using the Excel sheet by just giving some arbitrary number. I'm going to give an arbitrary number, minus 30. And I'm finding that I'm getting only 3.9 Newton meters of torque. Now, let me go to this solver. The way to go to the solver is go to the data tab, go to the solver, and here I'm telling maximize E21. That's what I said here. Maximize the torque. This button, I'm clicking here to say maximize. And what do I want to maximize? I want to maximize E21. How do I want to maximize it? By changing the angle. And this angle is E15. So I'm writing here by changing E15. And there is one more constraint. I'll talk about it later when we come to the speed and voltage block. Right now, just assume that there is a constraint. And now I will say solve. It has solved it. And I can say, okay. And it has given me the angle minus 11.7 and 4.2. I've got back the original angle, which is the optimum angle. Can you all see that? So without my doing trial and error, the Excel has already run a few thousand iterations in a fraction of a second and discovered that the angle is minus 11.7. And again, this minus 11.7 is only for viewing, that I've shown it like this. If you go to the Home tab and you want to look at it more accurately, you can say increase decimal by clicking on this. you know that the angle is minus 11.66034. So to that level of accuracy, it has already calculated it. But because it's a eyesore for us to see it like that, I'm just keeping it like this, minus 11.7. So do you all understand this? Is this clear so far? Let me end the sharing so that you can ask any questions you want. I can see the chat also. You must use the tool solver. Try to do it right now as we are talking. Change the angle to whatever you want and then see whether you're getting back the same angle by using the solver. So the solver is actually a way for you to find the correct angle. Once you find the correct angle, you can then input that value to your software, and this is how the software is written. Please remember that this tool can help you to write the software correctly. You can apply this solver repeatedly, and for different currents, you can get different angles, and you can make what is called a lookup table and put that lookup table in the controller software. So later on, when the driver chooses any current, the software will look in that lookup table and match the angle for that particular current and supply the angle. This is how the software works. What is called the MTPA algorithm. Is there any question about this? Please ask. 70% of the controller software is only this, nothing more. In 30% of the time, there is one more algorithm that will be used called flux weakening. We'll come to that later. But otherwise, in 70% of the operating conditions, this is what will be used. And in fact, in 80% of the motors that you find in the market, their design is such that there is no other algorithm you can use. You cannot use flux weakening in them. You can only use MTPA. All the BLDC motors, you can use only MTPA. In all the SPM PMSM motors, what is called SPM? Do any of you know? If you have seen the lectures, you will know. It is called surface permanent magnet. In all the surface permanent magnet motors, which means the magnets are pasted on the surface of the rotor, in all motors of that type, you can only use the MTPA algorithm. Only in a small special class of motors, which is called IPM, internal permanent magnet, PMSM, which means permanent magnet synchronous motor. Since permanent magnet word is coming again and again in the abbreviation IPM and PMSM, I already told in my lectures, video lecture, that it is abbreviated as IPMSM, means internal permanent magnet synchronous motor. Only in that class of motors, this other algorithm called flux weakening will apply. In all other cases, which is about 80% of the motors you will find in the market, which are called brushless motors or anything, in all of them, only the MTPA algorithm gets used, nothing else. So if you understand what we just now discussed about the solver, you have understood the entire algorithm of the controller. There is nothing more to it. Only if you come to the special category of motors called IPMSM, then there is one more algorithm which will be used in certain operating conditions. We will discuss that a little later. But I'm spending a lot of time because I have practically covered the entire motor control software, which is applicable to 80% of the motors that are used. So if you have any doubt about this, please ask me. It's a very important thing. And I'm trying to share again. Let me go back to the Excel sheet. You will notice that the torque comes from the magnetic torque and the reluctance torque, and the magnetic torque comes from what is called Xi. The Xi in turn depends upon the temperature. So you will see that out of the total torque, only a small amount of torque is coming from the reluctance, 0.2, whereas 4.1 is coming from the magnetic. And that dominant torque, which is coming from the magnetic, which means it depends upon the xi, is severely impacted by temperature. If the temperature is not 80 degrees, but only 45 degrees, you will find that the magnetic torque has increased to 4.3. So you know now that the temperature has a significant impact. I will not go into, okay, I will go into the KE part now, because the reason why I'm using KE is that when I have a motor and I'm trying to measure what is the magnet strength, I told you that the xi can be measured using a particular instrument. I have to pull out a magnet from the rotor and I have to measure the xi. What is the name of the instrument? Can any of you tell me? I already mentioned it at least 3 times, I think, in my talk. What's the name of the instrument that we use to measure the magnet strength? Do any of you remember? You have to be more attentive. I've told you 3 times. What's the instrument? How do you measure the resistance? I told you the different instruments used for measuring each of the motor parameters. How do you measure the resistance? Can anybody tell me? What's the instrument used? Okay, what is the unit of resistance? What are the units in which you express resistance? Ohms. And in our case, the resistance is very, very low. So what are the units we use? You can look at the Excel sheet and you will tell me. Milliohms. So we have something called milliohm meter. Milliohm meter is used to measure. How do I measure the inductance? I told you that we use something called an LCR meter. LCR stands for, L stands for inductance, C for capacitance, and R for resistance. Perfect. Somebody has answered, it's an LCR meter. And how do we measure the magnet strength? That's the question I asked.
The Gauss meter?
Exactly, Gauss meter. Actually, 10,000 Gauss is 1 Weber. So just like we use milliohms, if I want to measure or express magnet strength very accurately, then I can use Gauss. But Gauss is not the SI unit. So that's why you see in our Excel sheet it is 0.0120 Weber, which is a very small number, but I can express it in Gauss as 120 Gauss. So that meter is called a Gauss meter. Now, to use a Gauss meter is a very messy thing. I don't know how many of you have seen it. It is not a very straightforward instrument. I can just stick 2 probes and it will tell me the strength. It will throw some random number, and that number I have to then do a lot of complicated calculations based on the dimensions of the magnet, shape of the magnet, and so many other things. And the other problem with using the Gauss meter is that I have to first pull out one magnet from the rotor. That rotor will have magnets that are pasted on it. Now, if I pull it out, I cannot put it back. So it's a very destructive activity. It is very difficult to stick back the magnet unless I am a very expert manufacturer. If I'm just an ordinary user, it is very difficult for me to put the magnet back. So it's a very clumsy way of measuring the magnet strength. So normally what we do, again, if you look at the lecture videos, I've explained all this in detail. What we do is we measure something called the back EMF of the motor without even having to open. Without having to open the motor at all, I can find 2 important parameters, 2 out of the 5 parameters. I'll go back to the Excel sheet. I told you that there are 5 parameters about the motor that we are interested in measuring. These are the 5. Pole pairs, inductance, the D and Q axis inductances, then the magnet strength and the resistance. I can measure the resistance without opening the motor because the wires are coming out. Same way I can measure the inductances without opening the motor because the wires are coming out. I need to open the motor to inspect how many poles are there. I need to not only open the magnet but break away one magnet separately and take it to the instrument called Gauss meter. So these two fellows are my problematic fellows. I'll simply mark them in red. These two are problematic parameters because I may end up destroying the motor in the process. Even if I open the motor, normally the motor will be having all kinds of adhesive bond and other things in the cover so that water and other things don't seep in. So if I break all those bonds and open it, later when I put it back, it will not be a good motor. It may easily get damaged in the slightest of rain and shower and something. So these two things, if I want to measure, I will usually end up damaging the motor. So the simple way to measure these two things without damaging the motor is that I will take the motor that I want to measure, I'll connect it using what is called a coupling to another motor, to the shaft of another motor. I'll connect the shaft of this motor to another motor, which I can make it run at some known RPM. I can make it run at 1000 RPM, or I can make it run at 1440 RPM or 3000 RPM, whatever. At some known RPM, I'll make that motor run. And when that motor is running, because its shaft is coupled with this new motor of mine, this motor will also run. This motor is running not because of electricity, but it is running because it is being rotated by the other motor that I have connected with it. It is being mechanically made to run. Please note that. And if I mechanically make the motor run, then it will start producing electricity. It will act like a generator. So if I take the wires that are coming out of the motor and connect it with an oscilloscope, then actually I'll find a sinusoidal waveform. If it's a good motor, I'll find a sinusoidal waveform. If it is not very good, it will be a slightly distorted sine wave, maybe with some noise and spikes thrown in. And if it's what is called a BLDC motor, it will be a very, very bad shaped wave. It will be like a sine wave that is made of steps, 3 steps up and 3 steps down. How do I show it? I'll show it here. It will be like this. Like this. It will be something like this. It will look like this. Okay. The sine wave will be approximated like this. This is what you will see in the oscilloscope. When actually what you are trying to look at is this is the x-axis in the oscilloscope, and just to make it clearer, let me format it. So you will get a sine wave which looks somewhat like this. If it is as bad as this, it means that you are using a BLDC motor. Okay. If it's what is called a PMSM motor, then it will be more like a smooth sine wave, but it may have a few spikes and distortions here and there. And if it's a really nicely built PMSM motor, like what we build here in IIT Madras, then you will find that the back EMF is perfectly sinusoidal, almost perfectly sinusoidal. It will be like a textbook example of sine wave. Then it's a very good, smooth running motor. Anyway, so this way of making the motor run by mechanically rotating its shaft and then capturing the waveform that's coming on an oscilloscope will tell us what is called the back EMF. This shape is called the back EMF profile of the motor. And when I look at the back EMF profile of the motor, the amplitude of it. The amplitude of a wave is what is the peak from the x-axis, this height. The amplitude of the motor is called the back EMF, and the frequency of it is called the electrical frequency. So the electrical frequency will be written as, I'm writing these things because many of you are not familiar with the concepts. It will be written as omega E. What happened? Omega E. And are you able to see it clearly? I don't know. So omega E is the electrical frequency. Now, since I know the RPM at which the shaft is rotating, if I divide that RPM by 9.55, as we earlier discussed, 9.55 is not a mystery number. 1 by 9.55 is 2 pi by 60. That's all. So instead of multiplying by 2 pi by 60, I can divide by 9.55. And that will be called as, let me write it here, Control C, V, and it will be called omega M. I can reduce this to 11. So omega, are you all able to see the screen? Should I zoom in a bit? Why is my computer so unresponsive? Okay. I'm not able to zoom for some reason. Okay. Now I can zoom. Okay. So I've zoomed a bit too much. Okay. So by looking at the waveform, I know what is the omega E. Since I know the speed at which I'm rotating the shaft, I know what's called omega M. And the ratio between omega E and omega M will be equal to the pole pairs, P. So without opening the motor, I can know what is the P. And if I know what is the amplitude of this, and if I convert that amplitude to, actually if I know the amplitude and I know the speed, then this is a very simple way. You can look at the equation here. If I know the, supposing I measured the amplitude at 2000 RPM, then whatever amplitude I got, I will divide it by 2 and say that is the amplitude per 1000 RPM, and that's called the back EMF constant. And if I know what's the back EMF constant, volts per 1000 RPM, then I can use this formula to back calculate what is the Xi, which is the magnet strength. So I can find the magnet strength without opening the motor. I can find the pole pairs without opening the motor. Both of these things I can find, P and Xi, without opening the motor. And I already told you that the other three things, LD, LQ and RS, I have to only measure using some instruments applied on the wire leads that are coming out of the motor. So in effect, without opening the motor, I can fully characterize all the electromagnetic parameters of the motor. So that is what brings us to the end of this block. Let me go back to the normal zoom, and we discussed this block called torque and current. And torque and current come, the torque is a result of, the current and the phase angle. And there is one selection of phase angle for which the current will be most optimum. And anyway, to even do these calculations, we need to know what is the Xi and what is the number of pole pairs. And since we cannot directly measure xi, we are measuring using this. So if you see here, 7.7, and if you see the xi here, the xi has come to something so long. So I'll finally tell you why it is so long. The suspense I'll break. What I did was I measured the back EMF because that is what I can measure experimentally. And then I want to find out what is the value of xi, which will give me 7.7. Now, if I enter manually here 7.7, then the relationship between this cell and the cell at the top, which is E5 for the xi, is broken. And I don't want to do that. So instead, what I'm doing is I'm going to goal seek via data and what if analysis, goal seek, and I can say make E25, that's what is given here, set the cell E25, let me now change it. It is now 7.7. Supposing I take another motor and measure it, and if I find that the value is actually 8, it is not 7.7, then I'll say it is 8, and I'll say you change it by changing the cell E5. Now listen, look carefully what happens to this number when I say OK. This has become 8, it is OK, and if I go to E5 and see what has happened to the xi, it was 0.0120, it has become 0.0125. But because it has come by the function called goal seek, which Excel has executed by doing thousands of cycles in a fraction of a second, it has computed it to great accuracy as this. Do you understand? So this is how I get. I don't normally know xi directly. I do it by back calculating from the back EMF. So that is why I put this block here along with the torque and current block. And you will also notice that the back EMF that I measured, I put here. But because the temperature has increased, the operating back EMF is lower because the magnet has become weaker. And the torque takes its reference from the operating xi, not from the measured xi. In other words, it is derived from the operating KE, operating back EMF constant, not the measured back EMF constant. Because the operating is what is the value at the particular temperature of operation. Now, lastly, before I sign off, just as a fun exercise, let me change this current to 60. You know that I already told you that the torque depends on the current. So you will expect that if I make it 60, the torque, which is 4.5, will increase to some higher number. Let us see how much it increases. It has become really high. It has become 8. But is this the best torque I can get for 60? No. Because the angle that is optimum depends upon the current. We already optimized this angle using the solver for 35 amperes. But now that we have changed the current to 60, we have to again optimize this angle for 60 amperes current and see what is the best angle for it. I can do that by little bit increasing. For example, I'll make minus 11.7 as minus 14. I have made the number a little bigger. Now see what happens to the torque. It doesn't change much. If I make it minus 20, it doesn't change much. It has decreased. Now, the simplest way to do it, rather than doing all these trial and error, is I'll just go to solver and I'll apply the same solver again. And I said that I'm getting the best torque at minus 16.8. It may appear to you that the torque hasn't changed, but the torque is in many decimal points. So the earlier angle of the present angle is giving you, okay, let me write over here. It is giving you 8.097504. Whereas the angle earlier was minus 11.7, and if I change that, oops, it has become 8.056742. You can see that it is decreased. So 11.7 degrees actually gives you slightly lesser torque than the other angle, which was 16 or something. Doesn't matter if we don't remember it, because we can always find it by applying the solver. Yeah, minus 17 almost. It's giving you a little bit more torque. It is giving you 0.04 or 0.05 more torque. Because we had rounded it off to the first decimal place, we thought that the torque is not changing. But Excel will tell you exactly what is that torque at which you will get the best torque. What is that angle at which you will get the best torque. So this algorithm, MTPA, is very, very important. I want you to remember that, and I want you to remember how to do it using the solver. And we already used goal seek to find the xi if we know the key. Of course, if I know the xi and I enter it there, automatically it will give me the key, because that is how the formula is. But since I'm going in the reverse direction compared to the way I've written the formula, I'll use goal seek. So this is about all that I have time to cover today. There is a lot more here. The steel loss is integrated, the thermal is integrated, and finally, if you remember, we started off, we started by assuming that the winding temperature is 45 degrees. This is an assumption we made. But the thermal tab is telling us that the actual winding temperature is 106. Now, how do I reconcile the two? And the way to do that, again, is a very nifty thing. I've got a goal seek at the bottom. If you come down, it says that if I assume winding temperature is 45, then there is a 61-degree difference between the two. All I have to do is apply goal seek. Goal seek, this, not E51, I will, yeah, E51. I'll make this cell equal to 0 by changing the assumed winding temperature, which I think is E9. I'll go up and select it so that I don't make a mistake. Yeah, E9 is the cell. I'll select that and I'll say OK. Then I find that the winding temperature is actually 127. And if I go to the thermal tab, there also it is matching, it is 127. Both the tabs are matching by using the simple goal seek. And if you remember, before we did the goal seek, it was 126. But after we reconciled, it has actually become 127. Can anyone tell me why it became more by one more degree than before? Why did it become more by one more degree than it was before? It's a very subtle point.
Maybe due to rounding?
It's actually not due to rounding. In this case, the difference is only 1 degree. Sometimes you'll have difference of 5 degrees also. Because when in the electromagnetic tab, if the temperature goes up from 45 to 126, which is what it should have gone up to, then the resistance increases. When the resistance increases, the heat increases. And when the heat increases, then in the thermal tab, your calculations have to be done again. Because originally the calculations were done with a certain assumption. And now the calculations have to be done again using another set of assumptions for a new resistance. So finally, this will be all these calculations will be done again and again till the two exactly match. So for the increased heat that comes from the increased resistance, the correct temperature at which the electromagnetic and the thermal will match is 127 and not 126. I hope I was clear in explaining that. So I think we are at the end of the session, end of the time. I did not cover everything I wanted to cover, but I have covered, whatever I have covered is what is used in 80% of the motors in the market, as I told you. all the BLDC motors and all the PMSM motors which are SPM, surface permanent magnet, they all use only this much. And if there is a more sophisticated kind of motor, which is called the internal permanent magnet, PMSM motor, then there is one more algorithm called flux weakening. All of these are discussed in the lectures. If you read them, and now that you have an introduction to how the estimator Excel tool works, you will be able to familiarize yourself with all the areas that we have not covered today also in the Excel sheet, and you will get better at it, and you'll be able to design any motor that you want. So,
Sir, I have
let me-
a doubt, sir.
yeah.
Sir, I gave the winding temperature as 55, gave gold 6, and automatically the winding temperature E9 changed to 53 degrees.
You gave a winding temperature of 55, okay, then,
55.
okay,
And here gold 6. Gold 6,
yeah,
it reduced to 53 degrees now, E3.
no,
E9.
let me do it again on the screen, 1 second, I'll just share the screen with you, share. So I am making this assumed winding temperature as 55 degrees, as you said. And I'm first of all going to the thermal tab, and I'm seeing that the temperature has come down to 109. The reason 127 degrees came down to 109 is because the resistance has come down at the lower temperature, so the heat is lesser. So purely from a thermal point of view, if less heat is coming, temperature will be lower. But this temperature is not matching with what I have assumed. That's my problem. So now I go to the bottom, this cell, correct?
Yes, sir.
And I go to goal seek, and I'll say change this value to 0 by changing E9 is what you gave, correct?
Yes, sir.
And now I'm saying okay. So this has become 0. That's okay. Now if I go up, it has come back to 127.
27.
Fine.
Okay, sir.
So no matter what you assume as a temperature, that is one of the beauties of this tool that I have given you, this Excel sheet. Wherever assumptions have to be made, you can feel free to make any assumption without worrying too much. And later on, you can use goal seek to reconcile everything. It will all happen before you can blink an eyelid. All the numbers will be correct, including the ones that you assumed wrongly.
Okay, sir.
If there are any other questions, please feel free to ask me. So if there are no other questions, then I will hand it over to Dr. Bhattacharya.
So he had some technical troubles and he got up. So we have to skip this meeting.
Okay, fine. Okay. So it doesn't matter that the session has ended. All the material relevant to the session has already been shared with all of you, and assignments have also been shared. I will encourage you all to go over the deck, look at the lecture videos. I think some of you went to the lecture video link and started looking from the very first video. Then there will be hundreds of videos for you to cover. You will never finish it. After you go to the link, please go to the tab on the left navigation pane which says week 7. And in week 7, go to the last 2 videos alone. And after that, go through all the videos in week 8. I am only asking you to go through the last 2 videos of week 7 and then all the videos of week 8. That is what is relevant to this topic. Of course, if you want to look at all the other videos that are there, you are welcome. Some videos pertain to batteries, some pertain to chargers, and so on. So they are all of interest. But I'm saying if you're interested in motor and controller, then only these videos you have to see. And wherever you think that the topic is something, topic covered in the video is already well known, you don't have to waste time. So a better way for you to go about is you just look at the PDF decks that I've sent you. I've sent you 4 sets of decks. And if you look at the slides in it, whatever you know, you can simply scroll through. It will be very simple. Wherever you think that you need some more explanation, then go to the relevant video. The slides I have given you are exactly the same as the slides that I'm presenting in the video, no different. So wherever you have a difficulty in understanding the slides, then alone you go into that video and get a clear understanding. And as you keep progressing, you will see that the assignments that have been given to you are also numbered in that same sequence as the sequence of the lectures. And you try to answer them, because if you try to answer the questions in the assignment, the same concepts that you understood will become more firmly grounded in your mind. You'll get a stronger grasp of the concepts. And whenever you finish all the assignments, please send them to Neetu, and she'll be able to tell you how much you scored. And after the 20th, we can also share the assignments with you, the solutions with you. We cannot share the solutions before that because it is part of a live ongoing NPTEL course, and we are not supposed to reveal the solutions before the last date for assignment submission for the students. And at any time in the future, you can reach out to me for any help you may want with any of the topics covered and in using this tool that I've shared with you. And I'll be very happy to help you in any projects that you're working on related to motors and controllers. Feel free to reach out to me. It'll be my pleasure. So thank you very much. Unless any of you have any specific questions, I'm signing off in the next 10 seconds. Thank you.